next one is where we're going to start. Function composition. All right. Function composition is noted using a little circle in between your two function names. So f composed with g of x. What that means is you're taking the g of x function, or whatever function is written second, and putting it inside of the first function. So you're replacing x in f with whatever the g of x function is. And g of x, really it's the y values from the g of x function going in as the x values of the f of x function is what's really happening there. With that function composition, since it's function stuff, we're going to talk about domain. It's a set of all numbers x in the domain of g of x, and I'll put that, being the second function in the statement. In the composition statement, it's the second function. Won't always be g of x. Sometimes it'll be a different one, because they may give you 4 or 5 of them and then tell you to do the composition with that. So the second function that's listed, all the x's that are in there, such that g of x is in the domain of f of x, or the first function. So what you've got to do really is you got to look at both the domain of both of the original functions, and then you're going to also look at the domain of the composite function. Yeah. All right. So we've got to look at all of that. So we're going to do some function composition, and we're going to look at those domains as we go. And sometimes it's pretty easy. Sometimes it's they've got some restrictions. You've got to know which restrictions matter is the big deal. So the first one, let's just take a couple of functions. F of x is 2x squared minus 3, and g of x is 4x. Two pretty plain functions, nothing really alarming going on there to worry about those. And if we're going to find f composed with g of x, so find and the domain. Find that composition and the domain. So finding the composition is not completely foreign to us. It's just plugging in one function into the other. So we're going to take the g of x function, the one that's listed second in the composition statement, and we're going to place it in for x in the first function. So that's taking 2, and instead of x, we're going to put a 4x in the place of it, because that's the g of x function, squared minus 3. And we're going to simplify that, because this is an algebra class. We want to try to make it as simple as possible, or look as normal as possible. So if we square 4x, that's going to be 16x squared. And then we can multiply that by 2 and get 32x squared minus 3. That's the composite function. Okay, so we found that composition. That's what it means to find the composite function. F composed with g is actually plug it in and work it out. All right. Now, the other part of the problem was to find the domain. Okay. So to find the domain of the composite function, we need the domain of f of x and the domain of g of x to help us find the domain of the composite function. Okay. So when we look at the original functions, are there any red flags when it comes to finding domain for those two? What are the red flags that could exist? What are the two things that we look for when we're talking about domain? Not necessarily, well, it's a certain exponent, but it's not in this problem. Square roots is one of the red flags. Are there any square roots in the problem? Neither of them have square roots. The other red flag would be a x in the denominator. Do these either of these even have fractions in them at all? No. So there's no red flags on this one, which makes it a super easy one to find the domain on, because the domain of f of x would be negative infinity to positive infinity, and the domain of g of x is the same thing, because there are no restrictions on those. Because there are no restrictions on either of those, there can't be any restrictions on the composite function. Okay, so the domain of our composite function would be negative infinity to positive infinity, or all real numbers, ever how you want to write that. Be able to bounce back and forth between forms there. There's interval notation. You could also have, x, all real numbers. That's also a possible, way of writing that. Same thing. We'll kind of hang out more in interval notation than the other. Okay. All right. So no restrictions on either. There can't be any restrictions on the composite function. All right. Let's do a little bit more difficult one. Example B. F of x is 1 over x plus 5, and g of x is 4 over x minus 1. A little bit more difficult here because it's fractions, and that makes anything more difficult, right? If it's fractions. So we want to find the composition f composed with g and the domain. And it doesn't matter what order you do that in. I'm going to find the composite function first and then go back and get the domain. If you want to do the domain first, it doesn't matter what order you do that in. It doesn't affect it any. In fact, I think it makes it make a little bit more sense on the composite domain if you've already found the composite function, because you can see where that came from. Okay, so let's find that composite function, f composed with g of x. And it's a little bit more difficult on the simplifying side of things because we're taking a fraction and putting it inside of a fraction. So that's not the funnest thing in the world, but it is something we need to be able to do. So we're taking this function and replacing x with it. Okay, so 1 over 4 over x minus 1 plus 5. And I'm going to put that in parentheses just so it highlights that is replaced x in the f of x function. We need to simplify that. You can't have a fraction inside of a fraction. That looks bad. So we want to simplify that in an algebra class. So how do you add two things together when one's a fraction and one is not? Make the other one a fraction. And to add fractions, we have to have what? A common what? Common denominator. So that's 5 over 1. It needs to be 5 over, something over x minus 1, because the first fraction has x minus 1 on the bottom. So to make that happen, you're going to have to take the 5 over 1, and you're multiplying the top by x minus 1 and the bottom by x minus 1. That would give us a common denominator. And I'm showing that as a separate step there. I would normally just write it on the original there, just beside it. Okay, and we're going to simplify that. So that's going to give us 1 over 4 plus 5x minus 5. All that's over x minus 1 now. Where did the 5x minus 5 come from? I distributed the 5 to the x minus 1 up here. That's where I got that from. And then simplify that just a little bit more. 1 over 4 minus 5 would be negative 1. So that's 5x minus 1 over x minus 1. And then I'm dividing a fraction by a fraction. Dividing by a fraction is the same thing as what? Multiplying by its reciprocal. So 1 times x minus 1 over 5x minus 1. And since that's multiplying times 1, it really doesn't change anything. So it's x minus 1 over 5x minus 1. There's our composite function there, the final answer. X minus 1 over 5x minus 1. Looks quite different than the two we started with. Which happens most when you get a fraction, when you got fractions in your original functions, it does make it weird on you. But there's our composite function. That's handy to have. Now let's work on that domain. So let's look at the domain of f of x. Are there restrictions on it? F of x being 1 over x minus 5. Or x plus 5, excuse me. Yeah, yes, because there's an x in the denominator. How do I find the domain of that then? Nope. What do I do to find the domain of a function where x is in the denominator? I set the denominator equal to 0 to find out what's going to make it mess up. So x can't be negative 5. Because negative 5 plus 5 would be 0, and we can't divide by 0. So the domain of f of x is x does not equal negative 5. And we're not going to write that in interval notation. It's easier just to leave it there. Because the domain we're looking for is the composite domain. We'll write it in interval notation, but we'll just leave that there. Okay? So there's the domain of f of x. We need to find the domain of g of x. Space here. Domain of g of x, we got g of x is equal to 1 over x, or 4 over x minus 1. Well, that would be x cannot equal what? If I said x minus 1 equal to 0, x can't be a positive 1. All right? Now, here's where we run into things we've got to answer questions to. Okay? We've got to know, when does g of x match up to the restriction on f of x? Okay, so that's the question. That's the key question. When does g of x equal negative 5? Restriction on f of x. That negative 5 comes from there. Because g of x is what's replacing x in the composition here. So when does g of x equal negative 5, or the restriction on f of x? That's the key here. And so what we would do is we'd set that equation up. We'd set the g of x function equal to negative 5. So g of x is 4 over x minus 1. When does that equal negative 5? So multiply by x minus 1. 4 equals negative 5x plus 5. Subtract 5. And that's going to be negative 5x is equal to negative 1. Divide by negative 5. X can't be 1/5. That's one of the restrictions. Okay, so when we go to build the domain for f composed of g of x, we need the restriction on the composite function and the restriction on g, because g was, g of x was the original. We got our x's from there. So the domain of that would be x cannot be 1 or 1/5. So let's write that in interval notation. It'd be negative infinity to 1/5, from 1/5 to 1, from 1 to infinity. These restrictions right here, this 1 and this 1/5, they're coming from the g of x function and then the composite function. Let's look back at our composite function that we worked out. Look at the denominator right there. What's the value that would make that not work? It's 1/5. It's the same. They match up. You don't have to have the composite function to get that restriction, but that's where it's coming from, is from the two original functions, where they're equal. The restrictions are equal to the I guess the domain part of the function. Okay, so that 1/5, that's where that's coming from. 1/5 would have came from that. So you could get your composite restrictions from the composite function, or you could get them from the two original functions, depending on what it's asking for. I show it both, doing it here. I can do it either way, but sometimes it doesn't even ask for the composite function. It just asks for the domain of it. So it might be a really tough one to work out. It might be worse fractions than this one was. It'd be a really tough one to work out. So you might not want to work out the composite function. You'd rather just do the domain parts to get your domain of your composite function. So
will it be the g of x and then the f of g of x?
Yes, it will always be the second function listed, their restrictions, and the restrictions on the composite function. That's exactly right, Robert. Good. So that's what we got to remember. Let's do one more of those, and then we'll move on to something else. Know what letter are we on? D, C. All right, so let's go. F of x is the square root of x plus 3, and g of x is 2x plus 5. Again, we're going to find f composed with g of x and its domain. So the composition, what's going where? G of x is going into f of x. So that's, 2x plus 5 plus 3. So we're taking this and replacing x there with it. And then simplify that. 2x plus 10. Or I wrote plus 5, that's a plus 3. 2x plus 8. That's the correct way. Get the right color. And there's our composition, or our composite function. That's good to know. Let's look at that domain. What's the domain on g of x? Are there any restrictions on g of x? No, so it's x. It's all real numbers. Put it backwards. Dyslexic today. And then domain on f of x. Are there restrictions on it? Yeah, I got a square root. So what are my restrictions there? I've got x plus 3. What are the kind of numbers that I can take the square root of without something crazy happening? Yeah, those are, but what kind of number is 4? It's positive, right? Can we take the square root of 0? What's the square root of 0? It's 0. Yeah, you can. So remember the rule for when there's a square root, you set it greater than or equal to 0, whatever's under the square root. So set that. X has got to be greater than or equal to -3 in f of x. So what we need to know is when is the second function fitting that. So when is g of x greater than or equal to -3? That's going to be our composite function domain. So we set 2x plus 5 greater than or equal to -3 and solve it. 2x greater than or equal to -8. divide by 2. X has got to be greater than or equal to -4 for a restriction of that. Okay, so domain of f composed with g of x would be from -4, including -4, up to infinity, based on that. And if you look at the function composition there, that the square root of 2x plus 8, the same rule applies up there. If you did that, it's still got to be a 0 or positive. So if you set that greater than or equal to 0 and solved it, you end up with the same problem that you did down here. You got 2x is greater than or equal to -8. It's the same answer, yet x is greater than or equal to -4. Those match. They should. Okay. You could, yes, absolutely. Absolutely. If you've got to find the composite function, you can use the composite function to help you get your domain. You've got to keep in mind, though, on your domain of your composite function, you need the second function's domain, which the second function on this one, did it have restrictions? G of x, it didn't have any, so it didn't change this any. So it was only the restrictions of the composite function that gave us, the -4 to infinity. I don't think you're going to see double square roots. You might see one with a square root and one not. I don't think you'll see a double square root out of that. It really just doesn't get much different than what the examples I've shown you here. They're not going to get much more complicated than that at all. Just some fractions involved. All right. Let's do a quick function composition with numbers. One thing that you've got to be able to do here is find the composite function value. So let's say we had f of x, something simple like 3x minus 5, and g of x is something like -2x plus 7. And they want us to find f composed with g of 4. With this, you do not have to find the composite function. You can if you want to. We're not worried about domain here. All we're worried about is finding a number answer. F composed with g of 4, positive 4. That's the x value. And what you would want to do is think, oh, well, that just means take 4 and go here first and work that out. So g of 4 is -2 times 4 plus 7. And that's going to give me -8 plus 7, which is -1. So the y value that goes with the 4 is the x value. The y value that goes with it is -1. We're going to take that and put it in for x in f of x. And that's going to get us our composite function value. 3 -1 minus 5, which would be -8 as a final answer. So this gives you the x value for this one. Work that out, get the y value, and then go to the next one with that and plug it in for x. Okay, so x values first, y values go into the next one. It'd be that right there is your final answer. Final answer is what you're looking for there. You might see it written maybe like this, where you've got a table and you got 3 things going on here. Maybe you got x is -2, -1, 0, 1, 2, 3, and then f of x is written here, g of x is written there. Let's say we had 5, 11, 17, 23, 29, 35. Okay, and then g of x was, maybe it's -6, -2, 2, 6, 10. I didn't pick a good number. Let me get a better. It doesn't matter. I'll just make this last one work. 11. Doesn't matter. All right, so let's say they said find f composed with g of 3. Okay, so what's the 3? It's the x value for g of x. What's the y value that goes with that? 11, and I didn't pick a good number. Let me pick a better number because I just made this up on the spot. Let's do g of 0. That's a better one. All right, so what's the y value that goes with that? 2. Now we're going to use that 2 as what in the f of x? It's going to be the x value now. So we go to the x value of a 2, gives us the y value on f of x of 29. And that's our final answer. So that maps to that. This goes up here to this, which maps to that. It's like chasing it around with the functions. So you work backwards. You say, okay, this is the x value, goes to the y value with this guy, so 0 to 2. Then that becomes the x value. So back up here, goes to the y value for f, and that's the answer. It's mapping it backwards through that. So that's they do present you a few problems like that, I know, in the book, and then on the. I've actually seen that on the final. It hadn't happened very often, but I've seen. They do, yeah, that's right. They basically do give you the answer. You just got to chase it around till you find which one they're talking about. So, okay. So that's section 6.1, is composite functions. Let's get into section 6.2 and talk about one-to-one. Functions. One-to-one functions. One-to-one functions do not repeat x or y values. To be a function, you can't repeat x values. To be a one-to-one function, you can't repeat y values either. Okay. To be one-to-one, that means one x goes to one y, and no other x can go to that same y value. And that means that puts you to be one-to-one, where one x goes to one y and one y goes to one x. They only match up. They're unique pairs. I guess the best way to put that. So they're unique pairs. All right. So is the relation 1 to 1? All right. So let's answer this kind of question. 1-to-1, and we're dealing with a set of ordered pairs. So that's a relation, is a set of ordered pairs. So let's say we had 2, -3, 6, -8, 11, 5, and 15, 1. And that's our set of ordered pairs. Is that a one-to-one relationship? No x values repeat and no y values repeat. So for this particular set of ordered pairs, it is one-to-one. So that'd be a yes. Okay. Where it gets a little bit more difficult is when they don't give you a list of ordered pairs, but they give you a representation of a list of ordered pairs in the form of a graph. Maybe it looks something like that. There's a higher degree polynomial, maybe from chapter 5. And they want to know, is that a one-to-one function? So to be a function, does anybody remember the test that we used to decide if a graph was a function? vertical line test. This would pass the vertical line test easily. It is a function. But to be a one-to-one function, you use what's called the horizontal line test. And it's the same rules. If it hits it more than once, it fails. So does this, if I put a horizontal line on this, there's a good spot. It hits it twice. So horizontal line test says, oh, this one's not one-to-one because these two spots have the exact same y value. They've got different x values, but the same. So that's a repeated y value. So the horizontal line test tells us that this is not a one-to-one function. So no. Yep. Example C. Trying to draw a better looking graph here. Something like that. Some form of a cubic graph there, x cubed somehow. X cubed plus 3 or something like that. Does that pass the horizontal line test? Yeah, there's no way, I could put a horizontal line in a lot of different places here, none of which crossed it in more than one place. So this passes it. So this is, yes, it's one-to-one. All right. Now, even more difficult maybe is if they give you this function, f of x is equal to 3x squared minus 5x plus 7, and say, is that one-to-one? How can I check that? Graph it. Absolutely the easiest thing to do is graph that. Graphing calculator, go to y equals 3x squared minus 5x plus 7. And when you graph that, hopefully you see that it's a parabola. And would that pass the horizontal line test? It would? I don't think it would. It'd pass the vertical line test. It is a function, but it would not pass the horizontal line test. So that's not a one-to-one function. Anything that's x squared, a parabola shape, is not going to be one-to-one. Fails the horizontal line test. A little bit more difficult one is maybe you got something with a cubed. A little tougher to see. Maybe you got 3x to the third, plus 4. Something pretty simple like that. But still, to check if an equation is one-to-one, the best way to check is graph it, because you could spend forever checking ordered pairs. The graph is just a representation of those. So we should be able to maybe recognize what's going on here. What was it? Plus 4. Graph there. And it looks like it gets pretty flat there at 4. But I argue that it's not perfectly flat. If I zoom in to that spot, press the up arrow here until I get close to it. I think you'll see, yeah, it's close enough. It gets there eventually. All right. It's not perfectly flat. There's still a little bit of a flat spot in the middle, but it's still, if I zoomed in even further than that, it's still not perfectly flat. So this would pass the horizontal line test and be a one-to-one function.
Is there a way to check algebraically?
Algebraically, if it's one-to-one, other than looking at those places where you think it's flat, checking those ordered pairs, like get really, really close to 0 and check some ordered pairs there. Like if I checked positive 1/5 and plugged in a negative 1/5, did they get me the same y value? They shouldn't get you the same y value. They should get you a different y value. Just not. That would be the only algebraic way, the only test that you could do there. They're not going to get too borderline on you on this checking whether it's one-to-one or not. Okay. All right. Now, inverse functions. Inverse functions exist for one-to-one functions. Inverse functions. Swap the domain and range x, y. Okay, when you're talking about an inverse function, one-to-one functions, their inverses are functions. That's what puts these in the same section together. Inverse functions swap the domain and the range. So that's why it's important one-to-one functions that they're one-to-one and their inverses are functions, because the x's nor the y values repeat out of that. So when we're talking about inverses, we're talking about swapping x and y. Okay, so let's look at finding the inverse. So find the inverse. So example f, say f of x is this set of ordered pairs. -3, 6, -1, 7, 2, 13, 5, -8. That's a one-to-one function because none of the x values repeat, none of the y values repeat. So I know it has a inverse that is a function. So the inverse of that swaps the domain and range, or swaps x and y. So what's it do to those ordered pairs? Just flips them around. 6, -3. 7, -1. This is the easiest stuff we do. It gets harder from here, but now the notation for that f inverse is written like that. It looks like a little -1 exponent there by the f, or whatever the function name is, and it's read f inverse of x. But it looks like a -1 exponent. That's all it looks like. When it's ordered pairs, that's the easiest thing there is. It's not going to be ordered pairs too often. But the idea is still the same, okay? That it swaps x and y. So let's look at a representation of ordered pairs in the form of an equation like this. Here's a function, 6x minus 7. I'll go ahead and tell you it's one-to-one. I know that already. I'm giving you that information right now, that it's a one-to-one function. You could check it by doing what? Graphing it, checking the horizontal line test. You'd know that that's a one-to-one function based on that. What we want to do is find the inverse of that. So the inverse, f of x is the same thing as y, right? Y'all remember that connection. So this is really what the equation is starting out. The inverse swaps x and y. So we're going to do that with our equation. Then we're going to get y by itself again. Okay, so we swap x and y, then solve for y. So add 7. X plus 7 is equal to 6y. Divide by 6. So f inverse of x is x plus 7 over 6, or you could write it x over 6 plus 7 over 6. Those are the same thing. That's probably how your book's going to do it. It's equivalent. It really doesn't help any to split it on this one. Where it might help to split it is if that was like x plus 12 over 6. You could divide. If you split it up, the 12 and the 6 would divide and make a 2 there. It might make it look better. But stopping right there is fine with me. So it swaps x and y. You solve for y again. You got the inverse. Now, you know they're not going to stay that easy either. So let's go to one that's much more difficult. We'll just go ahead and jump off in the deep end. 85 degrees today. That's what you would do in the pool if it wasn't freezing cold. We're going fishing. Let's just go ahead and cast out and try to catch a big one. Let's get a fraction one. F of x is equal to 2x plus 1 over x minus 1. And they're going to tell you that x can't be 1. Why do they tell you that? because it's a fraction, right? It's got x in the denominator. What's the thing that x can't be? 1. That's given to you. You're not going to have to find that. Just if they put that out there, you know the reason it's there is because it's a fraction. It's really the only reason it's there. All right. So finding the inverse, we're going to swap x and y. So this is going to be x over here, but both of those places on the right side are going to turn to y. So that's 2y plus 1 over y minus 1. Definitely a little bit more difficult. Got two places where y is at. So it's in a fraction here. So to get rid of the y in the bottom or to move it out of the bottom, what do I have to do? Or what could I do? I could multiply by the denominator, and it would cancel it out there, and I'd have only y's in the numerators now. And that'd be xy minus x. So on the left side, I just distributed x to both of those and got xy minus x. 1 times x is x. X times y is xy. On the right side, the bottom part canceled out that. That's why I didn't multiply times the 2y plus 1, because it was gone before it got a chance to. Okay? Now, here's the difficult part. It's getting the y by itself, because it's in two different places. It's got something beside it on one side that's an x, and the other side's a number. Those aren't like terms. So it's hard to get those to be together. So what you want to do is you want to move everything that's got the y over to one side, and the stuff that doesn't have a y goes to the other side. So I'm going to move this x on the left side over, and that's going to give me xy is equal to 2y plus x plus 1. And then this guy has got a y. So I'm going to move it to the over there with that xy. So I'm going to subtract it. You can do that in one step and do it in two. I took 2. So I have xy minus 2y is equal to x plus 1. All right. Now, believe it or not, all it takes is an Algebra 1, in high school Algebra 1 trick to get the y out of there. Does anybody have any idea how I could do that on the left side? Greatest common factor. What do both of them share? Y. So the greatest common factor would be a y. So because the y is on both of them, I pull it out to the front, and that just leaves me an x minus 2 inside of there. Now, what's going on between the y and that parentheses? What operation do those parentheses indicate? Multiplication. The opposite of that would be division. I want to divide by the part that'll leave y by itself. What do I need to divide by? The stuff in parentheses. If I do that, there's y by itself, and there are all the things that have x's. Whoops, that's a 2, not 3. Over there, hanging out. So looks like some sorcery going on, a little bit of hand waving and wand twirling and stuff, but that's our inverse. Okay. Not too bad, and it doesn't get much worse. If it's a fraction, it's not going to get any worse than that. I promise you that. But still something you need to be aware of. Let's look at one more find the inverse problem, and then we'll go to verifying inverses. Like I said, we got a lot of material today. G of x is equal to x squared. And they tell me that x has got to be greater than or equal to 0. Why did they tell me that? Because this is not a fraction, so I don't really have to have restrictions. Why did they have to tell me that x is greater than or equal to 0? What did I say earlier about anything that's x squared? That it won't be what kind of function? Well, think about the graph of g of x. the graph of x squared is this parabola shape. Is that a one-to-one function? Not right now, it didn't. But they said that x is only greater than or equal to 0. So what that does is it takes this half off. Now, is that one-to-one? Yes. So that's why they had to tell me that. So that it would make this a one-to-one function so that I could find the inverse of it. That's the reason that they tell me x is greater than or equal to 0. That's also going to come into play when I do the inverse stuff here. Not necessarily. No, it definitely wouldn't be the inverse. It'd just be the x is less than or equal to 0 side of things. So they could have given me that. I think you'll see what I mean when we go to do the inverse of this, and I think it'll make sense. So swap x and y. Not a whole lot of work going on here. What do I do to get y by itself? How do I unsquare something? Square root. But if I introduce the square root into a problem, what else has to be there? Plus or minus has to be there. So that's really y is equal to plus or minus the square root of x. Now here's where we got to think. Which part of that do I keep? This goes back to the x is greater than or equal to 0. Which part of that tells me the positive side? That's the positive side of things. So the inverse, g inverse of x, is the positive square root of x. If the inequality had been flipped around at the original problem, x is less than or equal to 0, then we would have used the negative side of the square root out of that. So that's where that comes into play. And that the inverse of this actually would be that kind of graph. That would be the graph of that inverse. That g inverse of x is that. So it's not the other half of it. That's the inverse. That would be the reflection of it instead of the inverse of it. We're going to see some verification of that in just a minute with graphs and algebra.
Basically, just two x.
Mm-hmm. Not quite. I'm saying for that particular problem, it ends up being that, but it won't always be perfectly that every time, especially if there's something in front of x on one of those problems. All right, let's look at verifying inverses. Verifying inverses. This is still same section. If f of x and g of x are, handwriting is not good today, inverse functions, then f composed with g, composition's coming back. Wondered why we did that. Equals x, and g composed with f of x equals x. If two functions are inverses of one another, if you do their compositions, it will turn out to be plain x. If it turns out to be anything else, they're not inverses of one another. Okay? So this is algebraic verification of inverses. Okay, we'll talk about graphical verification in just a minute. Algebraic stronger than graphical. It's easier, graphical is not always easy to see. It will be on the ones I show you, but it won't always be the easiest to see. So let's look at, I have no idea what letter I'm on, J. F of x is 2x plus 3, and g of x is 1/2 parentheses x minus 3. All right. We want to verify if these are inverses of one another. So we're going to do that composition in both directions. It's like, remember taking geometry in high school? You had to do those proofs. Nobody loved them. I liked them, but I'm a math teacher, so I'm supposed to. What it is, to prove that two things are inverses, you have to do both directions So if you ever had to prove this in a calculus class or something like that, you'd have to go both directions to show that. What you'll realize here is if they're not inverses of one another, the first direction won't work unless you mess something up. So you won't even have to worry about the second direction. If they are inverses of one another, the first direction works. The second direction should work as well. We're going to do both directions on this one and show that. So F composed with G. We're not worried about domain on this. We're just working it out. Just getting the composite function. So don't worry about the domain at all on the verifying inverses. So we're taking G of X and putting it into F. All right, so a lot of distributive property going on there. So that's like 2, 1/2 x minus 3 over 2. And then I'm distributing the 2 next. That'd be 1x minus 3 plus 3. And then what happens to those 3's? They cancel each other out, right? There's plain x, 1x. It worked. That means these must be inverses of one another. I need to verify that in the other direction. I need to do G composed with F of X. So that'd be 1/2. And then in the place of X, I'm going to put 2x plus 3 minus 3. This was a little easier actually to do, even though it's got a fraction in it originally. These 3's cancel each other out. That gets you 1/2. And then 2x is all that's left in there. So half of 2x would be x. Hey, it verified in that direction too. So these are inverses of one another by algebraic.
You said if it works out the first one.
It should work out in the second. If you do it right, it should work out in the second direction as well. Say that again. It should every time if they're inverses of one another. There would have to be a mistake made somewhere for it not to work out. Then you don't even have to go any further. If you didn't make a mistake in the first one, and that's where doing it in both directions kind of checks you that you didn't make a mistake or something there. It's both directions is more of a proof type situation. As far as what you're going to be presented with, it's going to ask you, are these two functions inverses of one another? If you check it in one direction and it works, it's going to work in the other direction. Verification, as far as that goes, you wouldn't have to show both directions for me. I'm going to show you how you can check with the calculator and get that. So that's the graphical verification that we're doing next. Graphical. Or graphically verifying. Inverses. And some people see these better than other people do. You've got a good spatial sense. You were good at shapes and things as a kid. You don't usually get better at that. You either are good at it or you're not by a certain age, is what they say. But verifying things with graphically. So this will be example K. Let's take the same two functions and look at it graphically, and then we'll do one that's a little bit more interesting than these lines. The lines are not very interesting. But let's say, and then G of X is 1/2 X minus 3. We know for a fact that these two are inverses of one another. If you graph both of them with the graphing calculator, so I'm going to go to white, I'm going to hit zoom 6 to go back to standard window, and then I'm going to graph these two equations and then one other equation with it. So we've got 2x plus 3 and then 1/2 x minus, parentheses, x minus 3. And then I'm going to graph y equals x. So here's the first one. Here comes 1/2 x minus 3. And then there's the y equals x line. That y equals x line is the definer. It's the mirror. If they reflect across that line, they're inverses of one another. If you look right here at this one, you flip this up here, it's on the blue line. They reflect across that line. Inverses reflect across the y equals x line. That's what you need to know there. Well, let me copy that picture and paste it there. Inverse functions reflect across y equals x. And, you know, that's graphical verification of that, right?
Will they always have a crossing?
Yes, and that crossing, well, they will have a crossing point, but you may not be able to see it on your screen. That's where it gets a little fishy on the graphical part. It may be somewhere off screen. You may have to zoom out to see that place. They should cross on that y equals x line though when they do reflect across there. I guess always is pretty strong. No, not always. They won't always have a crossing point, but they will reflect across y equals x always if they're inverse. So let's look at one that's a little bit more interesting and see what it looks like and see what's going on here. All right, let's look at this one. F of x, and let's do x cubed minus 27, and then g of x is the cubed root of x plus 27. All right, and you could do that algebraically, do the composition, and see what's happening. Let's look at it graphically and see what happens with that. So going to y equals, I'm going to clear out the two that I'd graphed before, and I'm just going to type in x to the third power and minus 27. And then this next one, clear it out and do the cubed root, which to get the cubed root, you can hit math and then go to number 4 and then do x plus 27 in there. So the math menu is where the cube root's at. So hit math and go there. And then I've already got the y equals x line in there, so I'm just going to leave it there. So there's the first one. And there's the second one. They're crossing each other. These two have a crossing point. It doesn't look like they're very interesting graphs, but if you zoom out, they're pretty curvy. About what's going on there. It looked pretty straight at the moment here, you know, in this little snapshot of it. But if you zoom out, they're cubics, so they got a little curve to them going on. But they do cross there, and you can see that they match up. It's real easy to see them matching up here. Most of the ones you're going to be asked to verify graphically for sure are going to happen pretty close to the origin. You're going to be able to see the reflection across there. But they won't necessarily always have a crossing point. They could have a crossing point, and if they do, it'll be on the y equals x line. That's let's see. If you had something like let's try this. Let's try x and clear that and do x squared plus 4 and then but we could only have one part of that, only one half of that, so we could do x is test greater than or equal to 0. And then that would be x minus 4, square root x minus 4, square root of x minus 4, and then parentheses, x is, again, greater than or equal to 0, because that's the positive side of that. I think I put the restrictions in there right. I may not have. I may have to have another set of parentheses there. All right. So pay no attention to this part. That's supposed to be the I didn't put the restriction in the right way on the first graph. Here we have, this is the x squared plus 4 graph. Here's the square root of x minus 4. Those are inverses of one another. it'll show up better if I'll hit zoom square, because the original window is not quite, same. That's a little bit better because you can see they match up here and here. It's a little, they don't cross, but they do match up. This is not part of the graph. That's where I didn't put the restriction in the right way. Syntax was wrong. I should have had parentheses around my x squared plus 4. But there's one that doesn't cross, but does reflect across the line.
So the ones that like we put it in, you get the curve right here, the curve right here, there's a gap in between the pair. For those things,
no, not necessarily. They're not always inverses. Sometimes they can be, but they're not always. All right. So we got graphical verification is the composition. What does the composition have to equal? X. If it equals anything else, negative x, if it equals x plus 2, anything else, it's not inverses. If it equals x, then they're inverses. Graphically, it has to reflect across that y equals x line. There's a relationship there. Okay, so that's section 2. Let's get to section 6.3. A little lighter lifting on this last couple of sections here. A little bit more solving equations kind of mode here instead of theory type stuff. So exponentials is where we're going to start. Exponential functions look like this normally. C a to the x. This is your initial value. This a here is your growth or decay rate. And then that x is the exponent. It's usually in time if we're talking about a real world situation. Savings accounts and banks, exponential growth on their money. It's a little different formula, a little bit more added to the formula here, but we'll get to that eventually here. But exponential, that's what it's going to look like. Now, what we want to be able to do is recognize if some data is exponential. So is the data exponential? Now, there's a couple different ways to do it. I'm going to show you the way that's best. One way would be to do like a scatter plot. Like you type in the x values, the y values in list 1, list 2, and make your calculator graph it. But the problem with that is that you're only getting 4 or 5 ordered pairs, and exponential growth and quadratics or fourth power look a lot alike when there's not much data. When there's a lot of data, like 100-something ordered pairs, they don't look very much alike at all. Okay, so that's where you run into the problem of doing the scatter plot. So that's the way that's possible, but it's not necessarily the best way. The best way is to actually just check the y values out of that. So that's what we're going to do to determine that. So get a table of values. You have something that's an x and a y. They may have something like years and money or something like that. It's x and y. X is on the left, y is on the right. Or x is on top, y is on the bottom. That's the way it's always going to be. And if you've got some sequential x values, which you will, and then you got some y values, what you can do is check the ratio of y values. It's not a slope, it's a ratio. Okay? So we're taking 10 divided by 5, that's 2. 20 divided by 10, that's 2. 40 divided by 20, that's 2. 80 divided by 40, that's 2. If it's the same every time, so you're taking the next one divided by the previous one, always. So second divided by first, third by second, fourth by third, and keep going from there. You're checking that ratio. If that's the same, and then this is your growth factor or rate. Okay, that's your growth factor / rate. Depending on what situation you're dealing with, what it's going to be. Now, that lets you write the equation. we can find out what C is by using one of the ordered pairs in the problem. The easiest one to use is 0, if you've got it. If you don't have it, just use one of the others. And I would use the 1 if I didn't have the 0, because that's the next easiest one. Because then you've got 5 is C times 2 to the 0 power. What's the 0 power? 2 to the 0 power. 2 to the 0 power is 1. Anything to the 0 power is 1. So that gets you the C, or the initial value was 5. Whatever X, if you've got 0, the ordered pair with 0 as the X, that's going to be the Y value is going to be your C. That's the shortcut to it. But you don't always have that in the problem. Sometimes you've got to do a little bit more to get there. We'll do another example there. One that you maybe don't have that. So we got -1, 32, 1, 8, 3. All right, let's do 2, 4, and 3, 2. All right, so here we got to be a little bit more careful because we don't have sequential X values the whole way through. We're missing the 0 in between the -1 and the 1, right? So we can't check that one, the 8 over 32, because that's not going to be sequential X values. We need sequential X values. So 1, 2, 3, we can check those. So that'd be 4 over 8, 2 over 4. That's 1/2. And that's 1/2. Oh, they're the same. So that would mean this is exponential with a growth or a decay rate of 1/2, because it's a fraction, small fraction. 1/2 to the X. I'll put 1/2 in parentheses just because that's normally how it's written. I know that's decay because that's a small fraction there. Growth's going to be a big number. Decay is going to be a small number. That's the base of the exponential. Okay? If it's a big number, it's growth. If it's a small number, it's decay. All right, so let's find the C. And again, I would use the easiest one possible. So I'm going to use the 1, 8. Y is 8. C times 1/2 to the first power. So that's 1/2 C is equal to 8. And that's just regular algebra. Multiply by the reciprocal. C would be 16. So our function is 16 times 1/2 to the X. And we can find that function based on the ratio being the same. If the ratio is not the same on your sequential Y values, then it's not exponential. And we're not testing for quadratic or cubic or anything like that. I'm not sure if this edition of the book asks for linear or not. Linear, you would test slopes. If it's not exponential, you might check for slopes if it's linear. We're not checking for quadratic or cubic or anything like that in this chapter. We're looking for exponential, and I think it does ask if it's linear. If it's not exponential, is it linear? And then you just take the slopes. You take the slope equation and work that out. Are they the same? All right. Now, let's solve some equations. That's the meat of this particular section, is solving exponential equations. That's where we hang our hat for this section for the most part, is solving these equations. And when you're solving exponential equations, you want to think exponentially. Like, don't think add, subtract. Think what exponent, what base and what exponent could I do here? So when we're talking about exponential stuff, we're thinking base and exponent is what we want to think about. So let's look at an easy one to start off with. 2 to the x plus 5 is equal to 2 to the 8th power. Exponential equations, the variable is going to be in the exponent. What you want to do is have the bases be the same. In this particular section, to solve it, the bases need to be the same. As we progress through chapter 6, We're going to learn how to solve the ones where the bases can't be made the same. Every one of them you see in this section should be able to bounce it to be the same base. Here the bases are already the same. So that means the exponents must be equal to each other. That if 2 to the x plus 5 is equal to 2 to the 8th, then x plus 5 should equal 8. And then we just solve that simple equation. X is 3. And we've solved it. Now let's do one that's a little bit more work on our part. All right. 2 to the x plus 1 is equal to 16. So we've got to think exponentially about 16. 16 could be written as 2 to what power? 2 to the second is 4. 2 to the third would be 8. 2 to the fourth would be 8 times 2 would be 16. So it's 2 to the fourth power. So then our equation ends up being what? Because the bases are the same now. So they go, yeah, it's just x plus 1 equals 4. So x would be equal to 3. Different equation, same answer. Think exponentially here. 3 to the 5x is equal to 81. So I'm thinking, okay, 3 is a base. 3 is a prime number, so I know I can't break 3 down any. 81, though, is 9 times 9. So maybe that helps. 81 is 9 times 9. And then 9 could be broke down to 3 times 3. So 81 is really 3 to the what? 4th power. And then our equation ends up being 5x equals 4. Divided by 5. We get a fraction as an answer, and that's quite okay. This one's one that seems, I've seen it give students trouble every time I've ever put it on the board. And I do it every time because I know you need to see this type of problem. Because our gut instinct is to think, oh, 8 is 4 times 2. But that's not exponentially thinking. Try again. 2 to the third. Okay? And 4 is 2 to the 4 can be written as 2 to the second power. 8 can be written as 2 to the third power. So that's how you need to think about this. Every time I've seen people do this, they will say, oh, well, that's 4 times 2 is what the 8 turns into, and it doesn't turn into an exponential type problem. So they mess up there. You've got to think exponentially that 4 is 2 squared, and 8 is 2 to the third power. And then you've got to think, oh, exponent rules. What happens with the squared and the 2x minus 1? What do they do? When you have an exponent in parentheses with an exponent outside, what's the rule? It's multiply. So that ends up being 2 to the 4x minus 2. And the same thing over here. So that's 2 to the 3x. And now we have the bases the same and the exponents worked out. And now we just set them equal to each other. 4x minus 2 is equal to 3x. I'm going to subtract 4x. Negative 2 is equal to negative 1x. X is equal to 2. So you got to think exponentially on these things. Get them Worked out. Example G. 1 over 27 is equal to 9 to the 2x. This one gives folks a fit a little bit too, because the fraction involved. How are 9 and 27 related exponentially? Three times 9 is 27.
How would you do that?
You tell me. Exponentially, 27 is what? Three to the third, right? So this is 1 over 3 to the third. 9 is 3 squared, right? Now, what can I do to that to bring it up to the top? Nope. How do I rewrite 1 over 3 to the third power so that it's not in the denominator? No. Make it a negative. That's 3 to the negative 3. And then on the right side, we multiply those exponents again. 2 times 2 is 4x. So anytime you need to move a exponent from bottom to top, change the sign of it. If it's positive, make it negative and it goes to the top. If it's in the top and you need to move it to the bottom, change the sign. Okay, and that moves it from top to bottom. And that gives us, 4x is equal to negative 3, and x would be negative 3/4. Okay. Let's look at one. 4 to the 3x squared is equal to 8 to the x. So this is similar to example, F. Similar to it. So we got to think the same way. Exponentially, 4 turns into what? 2 squared. Exponentially, 8 turns into 2 to the third. So that's going to turn this into 2 to the 6x squared is equal to 2 to the 3x. That would mean my equation is 6x squared is equal to 3x. And we've got to think, oh, that's quadratic. How do I solve that? Because it's got x squared in it. To solve a quadratic, what does it need to be equal to first? 0. I'm going to move the 3x over. So that's 6x squared minus 3x equals 0. Then I've got options. I've got quadratic formula that I could do. I've got a, b, and c is 0. Or I could do factoring. I'm going to do factoring on this one because it's got a GCF of 3x. So that'd be 3x and then 2x minus 1. And then I set each of those equal to 0. X equals 0. And then add 1. 2x equals 1. X equals 1/2. 2 answers for that one. So knowing how to solve higher degree polynomials, or quadratics mainly, is about as big as they're going to get in this particular section. Still something you need to be able to do. You can't drop that skill. Example I. Let's use a base E, because they throw this in there. E is just like a number. It is a number. It's the exponential number. E to the first power is like 2.715 something. Bunch of decimals there. it's kind of like pi. It's been used. It's used enough that it's got its own symbol. Used a lot in bacterial growth, cell division, that sort of thing. A lot of biological science uses the base e out of that stuff. So it works just like a number. So the setup is actually easier because you don't have to worry about breaking an e apart. It's already done. You don't have to say, oh, well, that's 2 to the 3rd power or anything like that. It's just base e. So that makes the problems a little easier because you just drop the e's and you got x equals -5. You're done. Where it would get a little bit more difficult would be one like this, where you had e to the 7x times e to the x squared is equal to e to the -12. It looks extremely hard because there's a lot of e's in there. There's multiplication, there's exponents on the exponents, and it looks like that's an extremely hard problem. But if you know your exponent rules, it's not. If you're multiplying things together that have the same base, what do you do with their exponents? You add them. Okay, so on the left side, that's really e to the x squared plus 7x. And the right side, nothing's really changing on that. And then what gets dropped? The e's. So it's just x squared plus 7x is equal to -12. And you just solve it like a regular quadratic. I'm going to get it equal to 0. X squared plus 7x plus 12. And then you've got quadratic formula that you can use. You could use factoring. I'm going to factor this one because I know it factors to be x plus 4 and x plus 3. That's going to be -4 and -3 as answers for that. If you did quadratic formula, you get the exact same 2 answers out of that. So it's still, solving a quadratic there. It's not incredibly difficult stuff there. It's just taking e as the base, and just remember your exponent rules out of that. Be no different if they had 2's on the bottom. Oh, that's the base. E is just a number out of that. All right, last section of the night. 6-4. Logarithmic. Logarithms are just exponents. That's all. That's what you need to know. Logarithms are just exponents. That's all they are. They look different. Their exponents written in a different way, but they're exponents. That's what they do. That means they work like exponents. That means multiplication becomes addition, division becomes subtraction. So it's logarithms, but it's exponents that we're dealing with. So what we're going to do first is we're going to rewrite the log function, and I'm abbreviating logarithm by just writing log, as an exponential. So we just talked about exponentials. One of the tricks every mathematician has in their pocket, in their toolbox, is taking things that are new and making them look like things you've done before. Like the last problems we did. We took exponential problems, made them look like problems we've done before by using some rules. Okay? So with logarithms, that's a new thing. We're going to take them and we're going to rewrite them as exponentials. And that's going to help us today when we go to solve some equations. So first example, here's a logarithmic statement. Y equals log base 3 of x. So that's a base 3 on the log. So it's like a subscript. Now, here's how it works. That's our base. That's our exponent. Okay. Logs are exponents. That means logs are equal to exponents. Logarithms are equal to exponents. The base of the log is the base of your exponential. That's all there is to that. This base gets this exponent. It equals whatever in here. Always. So you can rewrite a log as an exponential. And that's going to help us when we go to solve some equations. Let's take this one. Log base 2 of x is equal to 3. Log base 2 of x is equal to 3. Base exponent 2 to the third is equal to x. We're gonna work that out later on. So that right now we're just rewriting it. We know that's 8, right? 2 to the third power is 8. We know that. But this is just rewriting a log as an exponential so that it looks like something we've already done. Log base 5 of 1/25 is equal to x. What's our base? Which one? 5. Good job. What's our exponent? Logs are equal to exponents. The x is our exponent. What we're taking the log of is what it's equal to. Another. Throw this in there. Natural log, ln, is what that is. ln, your calculator, your graphing calculator has an ln button. It's the natural log. What it really means is log with the base of an e instead of a number, instead of like 2. They're never going to write it like that with the log base e. They're going to write ln, natural log. But it's log base e. So when you're rewriting it as an exponential, that's e to the y equals x. Yeah, that's what I'm saying. Is this is really that. Those are the same. They're going to write it ln, but it's log. You think about it. Oh, that's log. That means log base e is what it means. So if we did another one, natural log of 8 equals x. Good job. Yeah, perfect. But you can go straight there. Now this one is log of x equals 3. So they don't write a number there. There's an understood number to be there. No. 10. Log base 10. Because our number system that we're in is a base 10 number system. You count. The reason it's base 10 is 10 to the 0 power is the ones digit. 10 to the first power is the tens digit. 10 to the third power or second power is the hundreds digit. 10 to the third power is the thousands digit. We're a base 10 number system. So when they write log with nothing written there, they're saying, oh, that's log base 10. So that'd be 10 to the third power is equal to x. So they're never going to write that 10 there. On your graphing calculator, there's a regular log button down here on the left-hand side. That's log base 10. It's what's called a common log. The natural log and log base 10 are common logs in that they're used more than anything. We're in a base 10 number system, so log base 10 is used a lot. Base 2 number system, that's binary. If you think about electronics and computers, that's ones and zeros. So that's binary 2 things. Hexadecimal, that's 6 places. That's used in some computers and coding and all that fun stuff there. Involved, but we normally work in a base 10 number system. So that's why log with nothing written there is log base 10, because we're in a base 10 number system. That's where we live. Different societies over the course of history have used different number base things, but base 10 it seems to be where everybody's kind of stuck. for the last several hundred years, thousands of years probably. Base 10s makes counting easier. Sure makes all our place values a lot easier. Or it seems like it makes sense. I guess if we were base 6 or base 5, we'd get used to it. It's because we wouldn't know any different because we didn't do anything different. So base 10, if it's plain log, it's base 10. All right, so let's go the other direction. Let's take the exponential as a log. What letter are we on? G. So we start out with 3 to the x is equal to 27. What log base would we be using? Log base 3 of 27 is equal to x. So we're just going the opposite, or we're going in reverse here. The inverse is really what we're doing. Inverse operation. For an exponential is a log. The inverse of a log is an exponential. That's how that's worked. That's why this is all in chapter 6 together. We talked about inverses earlier tonight or this afternoon. It's still daylight outside. I'm not used to that yet. So we talked about inverse functions. Logs and exponentials are inverses of one another. That's why this all goes together. Let's say we had a to the 4th is equal to 24. So this is kind of more of a theory type thing. You wouldn't be able to work this out very much. But what log base do we have here? Log base A. Perfect. That's it. Ten to the x plus 1 is equal to y. I'll rewrite that as a log. And we know that's log base what? 10. We don't write the 10 there. We just know it's there. Okay. That'd be that. No, we're not doing anything else to it at the moment. We're about to evaluate some and actually do some stuff with some. But right now we're just rewriting them. E to the square root of 2 is equal to y. That's a fun one. E turns into what? What's the log that goes with E? Natural log, ln of y is equal to square root of 2. Natural log is log, remember, is log base E. So ln is how you're going to see that written. It's log base E. That's really not a really good way to explain that. Natural log, E is the exponential numbers, like it stands for like 2.71 and some change. It's kind of like pi. It stands for a certain number. It's used enough in, I think this is when you stepped out, that it's used enough in biology and various other sciences that it got its own representative, like pi did. Pi was used enough in geometry that it got its own. Okay, we're going to call it 3.1459 and a whole bunch of numbers after that. We're going to call that pi. Well, E happened enough. They're like, oh, we're going to, instead of writing that number out all the time, we're going to call it E. Why they picked E, I don't know, but they just did. Whoever they is. Not sure who gets the distinction to be that person. All right, so let's look at evaluating some. And I'm going to evaluate them without a calculator. Obviously, you can do it with a calculator. I'll show you how to do it with a calculator as well. But I'm going to show you how to evaluate these without one, using the skills that we just talked about with exponentials in the previous section. All right, log base 2 of 16. They're just going to give you a problem like that. They're going to say log base 2 of 16. And and say evaluate that. And what I do to evaluate that is I set it up as an equation like that. I just say, oh, I don't know what it is. I'm going to say it's equal to x. And then I think, how can I rewrite that as an exponential? 2 to the x is equal to 16. And now it becomes a problem just like what we did in the previous section. Because I can make 16 turn into 2 to the 4th power, right? So x is equal to 4. So that means this equals 4. With your graphic calculator, you guys got a great piece of technology in your hands that can do some of this stuff for you. So with a graphing calculator, just from the regular calculator screen, if you'll hit the math button and then just press the up arrow, you should find this thing called log base right there. So log base and hit enter, and it puts a blank there for the base of the log. So we're doing log base 2 of 16, and hit enter, and it should give you 4 out of that. So it'll do some stuff for you here. It can be done without a calculator for certain numbers, and then there are times where if it had log base 2 of 15, we can't do that without some help. That's where a little computer-aided incentive could help, but it's not always a necessary thing. So JKL log base 4 of 1/64. Again, this is how I think about that. I was like, 4 to what power is 1 over 64? I happen to know that 64 is 4 to the negative 3, or 4 to the 3rd, and then it's a fraction, so I'll make it negative. I know that that's negative 3. I've done a billion of these in my life. That's why I'm faster at it. I actually just taught this in my high school course last week, so I'm really adverse at it this week because it's really fresh on my mind because I've done a bunch of just weird, tried to throw weird numbers to them to make them think. But again, calculator can help you. You're going to hit math, up arrow, go to log base, and then you put in the base that you're using. We're using a base 4 this time of 1 over 64. Negative 3. It can help you there. It's handy to know. Not necessary that you have the calculator to do it, but I just want to know it will do it. And you've got a great piece of technology in your possession for this course. Okay. All right. Let's look at the next thing in logarithms, and that's the graphs and domain. You cannot take a log of a negative number. That's important to know. Okay, so that means the domain of a logarithmic function has to be positive numbers only. Okay, so it's a lot like square roots. The only thing is you can't do a log of 0 because you think about it. Can I raise 2 to a power? Like 2 to what power gives me 0? Well, 2 to the 0 power is 1. But 2 to the negative 1 power would be 1/2. So no matter what I do, I can't turn that answer negative. And I can't turn it into a 0. Whatever number the base is, I can't turn it into a 0, and I can't turn it into a negative number. So when I'm looking about functions, they have to be positive only. So can't be 0, can't be positive, or can't be negative. Can't be 0, can't be negative. So when we look at a function and we want to state the domain, log base 2 of x plus 3. That's the function we're going to deal with first. example M. All we really have to do to find that domain is say, oh, well, x plus 3 is greater than 0, and solve it. And what in the world? Okay, cord game partially unplugged. No red or not much red or green going through there, just blue. All right, so we set that equal or greater than 0 and solve it. X has got to be greater than -3. So the domain is from -3 to infinity. Let's think about the range. What's the range? What's that dealing with? Like generally, what is a range in graphs? Domain is x values. We know that. Range is dealing with the y values, okay? The best way to think about the range or even discuss the range is to look at the graph of the equation. So we're going to graph log base 2 of x plus 3 with our calculator. Y equals, and then I'm going to clear out all this other junk that we were doing earlier. And then I'm going to hit math, up arrow till I find log base. And I'm going to put a log base 2 of x plus 3. I'm going to hit graph. Okay. Now, where's that going toward? Like, it's going toward positive infinity. What about downward? It looks like it's stopped. I wonder if it actually has stopped. What's that value where it looks like it's stopped at? That looks like -3, doesn't it? Okay. Huh. Wonder what's happening at -2.99. I got a y value, and that's below where it stopped drawing. Here's one of the drawbacks of the graphing calculators. They don't have, a nice, incredible retina screen like your smartphones do. They run out of resolution. That line is still going. There's this stopping place on the domain at -3. Remember, the domain x had to be greater than -3, but it's still, the range keeps going. So the range is from -infinity to positive infinity. I'm going to give you a hint here. That doesn't change ever. It always will be from -infinity to positive infinity. Right. That's what I'm getting at there. That it's going to ask for the range. And I want you to understand that's the graph, that's the y values, but it doesn't change from -infinity to positive infinity. That's exactly right. You don't have to worry about that. All right. Let's solve a few equations and we'll get out of here. Just a couple here, and I'll kind of show you what I'm after. Log base 3 of 4x minus 7 is equal to 2. And then what you want to do to solve a log equation, turn it exponential. So let's rewrite this as an exponential. That's why we even did that at the beginning of the section. So that would be 3 squared is equal to 4x minus 7. What's 3 squared? It's 9. 4x minus 7 is equal to 9. And that's an easy problem to solve. That's 16 is equal to 4x. Divide by 4 is x equal to 4. Okay. Say we had log base x of 64 is equal to 2. This one looks weird because it's got the base as an x. But if we think about solving that as a logarithm, good job, x squared equals 64. And how we solve that? Yeah, you can take square root of both sides. Plus or minus 8, right? It's okay to have a negative base. You just can't have a negative inside of the log. So that both of those answers work. You do need to check your answers on these as you're getting them. It's not necessarily something that you're going to throw out a whole lot of answers, but you do need to check them. We need to do one where it doesn't work out real nice so that you've seen that. 2 to the 3x plus 1. This is the last one we're going to do. I know you're tired. We got a lot of information here tonight, today, this afternoon, this evening, whatever you want to call it. This one is written in exponential form already. I meant to write it in log form. Log base 2 of 15 is equal to 3x plus 1. That'd be how it's written in log form. I skipped a step there. It doesn't work out real good because you can't write 15 as 2 to a power, right? That's the problem. So what you do is you to get rid of that 2 as the base, you can take the log base 2 of both sides. So this is the trick to that. These two cancel each other out. Whatever the base is, if you take the log of the same base of that side, it gets rid of it. Cancels it out. And then that leaves you just 3x plus 1 is equal to log base 2 of 15. That's a log base 2 of 15 is a number. The calculator could find that number. I'm going to get x by itself first. And then I'm going to use the calculator to get a decimal approximation for that. So it'll be 3x equals log base 2 of 15, then the minus 1. I'm going to put that in parentheses so that you cannot subtract the 1 from the 15 because it's inside of the log. That's a common mistake that happens there. And then divide by 3. Log base 2, 15, minus 1 over 3. And you could get a decimal approximation for that with the calculator by just go to the home page. Math, log base 2 of 15, and then minus 1 on the outside. I'm going to get that answer, and I'm going to divide that by 3. I get 0.969 if I go 3 places. They don't get any more difficult than that, really, in solving these. Not any more difficult than that. If you want to look in your textbook, I'll note out some practice problems here. I've tried recording this, and it should go online so that you can go back and rewatch some of it if you need to. And then next week we'll get the other half of chapter 6. And yeah, that last section is kind of light. It's application problems where they give you the equation and say, if this happens, you plug that number into a certain spot and solve it. It's application problems. So there's 8 sections, but there's really only 7 where it's pretty heavy lifting. Number 11 through 111. And then 133 and 134. These 2 questions. I'm putting those on there, starting on those. I got an email today from the folks that make the final, and there's questions that are almost exactly like that are going to be on the final. That's why I'm starting, separating those out. These are very important. He made sure to mention that, which is not normal for them to do that. So I thought it'd be good for you.
You don't do it.
I don't make the final. No, it's made by the math department at the campus in Martin. There's 4 or 5 teachers that get together, and they put together a course final, and everybody, like the folks up there on campus take a final, and everybody that's at a satellite center takes a common final, and so it's all the same. All right. Guys, I appreciate it. Thanks. Y'all have a good week. Enjoy the